Hello everyone. Today we are diving into the fascinating world of thermodynamics, specifically focusing on the first law of thermodynamics. The first law of thermodynamics states that energy cannot be created or destroyed, only transferred or transformed. In simple terms, energy might change forms from chemical to thermal or mechanical, but the total amount of energy stays the same. Research suggests that when students apply what they know to a creative project, they are able to develop deeper connections and retain important information for longer. To make learning more engaging, we are using creative projects to reinforce our understanding of thermodynamics and model what our future students will be doing. These activities allow us to explore complex scientific principles in ways that enhance memory and comprehension. We are modeling our creative activities based on a 6-stage creative project for engineering and thermodynamics. The 6 stages are as follows: the challenge, generate ideas, multiple perspectives, research and revise, test your mettle, and then go public. In the challenge phase, students are presented with a statement or scenario that poses a complex objective for them. The challenge should be related to a major concept of that unit that students will come to understand in order to learn about their challenge. My challenge is connecting the first law of thermodynamics to thermoregulation. Thermoregulation is the body's ability to maintain its core temperature despite external temperature fluctuations. In the Generate Ideas section, students are provided an outlet for demonstrating their prior knowledge about the challenge. This serves as a baseline or pre-assessment. In Module 1, we completed a mind map breaking down how thermoregulation related to key thermodynamic concepts. The mind map lists all of the ways that the body will control its internal temperature and how it connects to the first law of thermodynamics. Let's dive into the first branch. The human body regulates temperature through heat transfer mechanisms that align with thermodynamic laws. Since energy cannot be created or destroyed, it needs to be dissipated by the body. Conduction occurs when heat moves between objects in direct contact, such as when the body warms a cold surface. Convection transfers heat through fluids like air or water, which is why wind can make us feel cold, or a warm bath can heat our skin. Radiation allows heat to dissipate as infrared waves, which is detectable with thermal imaging. Evaporation cools the body by absorbing energy when sweat transitions from liquid to vapor. Another key process that generates internal heat is cellular respiration, an exothermic reaction where the body converts food into energy. An exothermic reaction releases thermal energy as a byproduct. This contrasts with endothermic processes like sweat evaporation, which absorbs heat to promote cooling. Breaking bonds is always endothermic, while forming bonds are exothermic. If more energy is needed to break bonds than released, the reaction is endothermic. If more energy is released than required, the reaction is exothermic. Endothermic and exothermic reactions can be visualized using a reaction energy diagram, which plots the progress of a reaction against its energy change. Endothermic reactions, like sweat evaporation, show an upward curve where the products have higher energy than the reactants, indicating that energy is absorbed from the surroundings. In contrast, exothermic reactions, such as cellular respiration, have a downward curve, meaning energy is released and the products have lower energy than the reactants. Both types of reactions require an initial energy input known as activation energy. Enthalpy represents the total heat content of a system and plays a crucial role in distinguishing between endothermic and exothermic processes. In an endothermic reaction, enthalpy increases because heat is absorbed by the surroundings, increasing the total heat of the system. Conversely, in an exothermic reaction, enthalpy decreases since heat is released, such as in cellular respiration or combustion. Another key thermoregulation process is shivering. When the body is exposed to cold temperatures, involuntary muscle contractions generate heat to maintain core temperature. This process increases molecular motion, which in turn increases disorder within muscle cells, contributing to a rise in entropy. Entropy is a measure of energy dispersion within a system and determines how much energy is available to do useful work. According to the second law of thermodynamics, energy naturally spreads out meaning that in an energy transfer or transformation, some energy becomes less usable. This is why no process is 100% efficient, such as shivering. Most of the heat we want to warm our bodies is lost to the environment. Another important thermoregulation process is vasodilation and vasoconstriction. This is when the body needs to cool down, the blood vessels near the skin surface widen, increasing heat transfer to the surroundings. This process is driven by an increase in entropy and decrease in Gibbs free energy. Gibbs free energy represents the total amount of energy available in a system to perform work at a constant temperature and pressure. It is determined by the difference between enthalpy and entropy in the system. In the context of thermoregulation, vasodilation and vasoconstriction are physiological processes that can help regulate body temperature by altering heat transfer and energy distribution. The next step in the project is multiple perspectives. These are statements or comments from experts that help the student gain a better understanding of their topic and connection to the first law of thermodynamics. I chose 4 quotes from my project. Peter Atkinson, in The Law of Thermodynamics, a very short introduction, emphasizes that the human body is a thermodynamic system subject to the first law, meaning it cannot create or destroy energy, but must transfer heat to maintain equilibrium. Chitramthal, in Review on Modeling Approaches on Thermoregulation Mechanisms, outlines the 4 primary heat transfer mechanisms: conduction, convection, radiation, and evaporation. The quote highlights how the body exchanges heat with its surroundings. Additionally, Sherwood, in Science Daily article, explains that heat dissipation requires a temperature gradient, where the skin must be cooler than the core body temperature, ensuring effective heat loss through evaporation when other mechanisms fail. Further expanding on heat dissipation, Professor Garcia, in Exergy Analysis and Human Body Thermal Regulation, introduces a concept of exergy, emphasizing the evaporative exergy flow is crucial when ambient temperatures surpass the body's thermal neutrality point, making sweating the primary cooling method. The next part is to have students complete hands-on learning activities or to teach or reinforce important concepts. The lesson plan introduces students to a concept of heat transfer in the human body using a thermography video to visualize temperature differences. Through guided discussion, students develop models to explain how energy moves within the body, incorporating concepts like conduction, convection, radiation, and evaporation. Secondly, a POGLE or process-oriented inquiry-guided learning assignment helps students classify chemical reactions as exothermic or endothermic, refining their models accordingly. They are encouraged to work in groups and analyze data and graphs. Then students will perform endothermic and exothermic reactions in order to classify them. Peer reviews and reflection journals further enhance their understanding by encouraging them to identify gaps and make improvements. Students will then conduct a calorimetry lab to measure the heat of reaction in different substances, linking this to the concept of ATP. They also investigate evaporative cooling using wet and dry thermometers to understand entropy and heat dissipation. This connects to the concept of sweating. Virtual labs introduce Hess's law and enthalpy diagrams, allowing students to calculate energy changes in chemical reactions and cellular respiration. Throughout these activities, students build a comprehensive understanding of how the body generates, transfers, and then dissipates heat. All of the research and experiments will work towards the generation of a creative project. Students can decide to write a poem, draw a picture, or make a comment. This is an example poem that a student could create. This is a conversation between a doctor and patient about the first law of thermodynamics and how it can connect to heat stroke. You ran too far, you pushed too fast, the heat within you couldn't last, your skin was red, your breath ran tight, your body fought with all its might. But I was strong, I felt just fine, the height was high, the sun was high, but so was I. I wiped my brow, ignored the heat until I fell upon my feet. Your body's like a furnace bright, burning fuel to give you might. It takes in food, it makes it burn, yet heat must leave your body's relief. Conduction, take what's near your skin. A cool wind blows and pulls heat in. But when the air is just as warm, your sweat must help, it's nature's norm. I felt the sweat drip down my face, yet still I lost the cooling race. My heart beat hard, my head felt light, the world around me turned too bright. Your sweat was there to cool you down, but when the air's too hot around, the heat can't leave, it stays inside. Your core still burns, no place to hide. When sweat won't work, your body's trapped, your system fails, your strength is sapped. So what can I do? How can I fight to keep my body cool and right? Cool your skin, use ice or breeze, help convection work with ease. A cooling weave, a clever thread, can pull the warmth and cool your head. The first law states heat won't just go unless we help direct the flow. Energy is here but must be freed. Balance is the only key. Thank you very much for listening to my creative project on thermodynamics and thermoregulation.